Could those folks at the top just find some seats? Thanks. So hello everyone, welcome to the second lecture in our Carbon Smackdown series. My name is Jeff Miller and I'm head of public affairs. Over the last year you've probably heard a lot about carbon sequestration or carbon storage as it's more commonly called. There's been much less talk about carbon capture. Well, you can't store what you can't capture first. So today we present two lab scientists, Jeff Long and Nancy Brown, to help us understand how carbon capture actually can work. And as always, we will take questions at the end of the presentations. So we will start with Jeff. Welcome.
Thanks. So the mics are on. Yeah, great. So what I'm going to do is I'm going to start by telling you a little bit of the research that's going on at the lab involving trying to capture carbon. And when you see carbon capture or carbon dioxide capture, that's usually referring to trying to extract CO2 from power plant flue gas. But in addition, after myself, Nancy Brown will talk about the ideas of possibly capturing CO2 from the atmosphere, where it's much lower in concentration. And so why are we doing this? I hope all of you have seen this alarming type of data. So here is CO2 levels in our atmosphere rising very rapidly. We're at about 390 parts per million. And the scary thing about this is that if you look at a lot of different data, but here's ice core data, CO2 concentration in the atmosphere does track with temperature on our planet. And if I were Al Gore, I'd stand up on a ladder, but here is where we are now, 390 parts per million. We haven't been this high. In fact, we haven't been above 300 parts per million in the last 400,000 years. Okay, so this is really kind of frightening, at least to me. And so where is all this CO2 coming from? Of course, you know it's coming from burning fossil fuels. And so the major culprits in terms of CO2 emissions are currently China and the US. And all told, around the world, we're emitting about 30 billion tons of CO2 per year. This is an enormous, staggering amount of CO2 that's being emitted, and it's mostly coming from burning fossil fuels in power plants and also in cars. And so in the US alone, about half of the CO2 emissions are coming from power plants, and about 30% comes from the transportation sector. The bulk of that transportation sector involves passenger vehicles. And so if we want to stop this CO2 emission and try and bring back normal atmospheric conditions, then we really need to stop burning fossil fuels. However, there's no chance that you're going to really go without heat and power, electricity, or driving your car. And so while we're looking for this renewable energy to do all these things, we're still going to be burning fossil fuels for a long time to come. And so the idea is that we should try and deal with that at the main source of CO2, which are these power plants. And so the idea here is that this will be a stopgap measure while we develop renewable energy technologies, but we're going to try and stop that CO2 that's being emitted from the power plants. And so that's going to involve taking the CO2 out of the exhaust gas from producing the power, transporting it usually by pipeline to some site where it can then be injected underground and stored underground for hundreds, if not thousands of years. Right, so that's the hope. And in this process, there's a huge cost in terms of energy. And so overall, with our best technology, this is going to cost about 30% of the energy that's being generated in a power plant to do all of this. And of that 30% energy penalty, most of it is in the capture process, in the method of extracting just the CO2 from this flue gas so that we can put just that underground. We don't want to waste all of our energy on compressing all the other components of flue gas, nitrogen, water, and putting that underground. We just want to focus on the CO2 and putting CO2 out of harm's way. And so this energy cost is what I'm going to tell you about our efforts to reduce that cost. And so in one of these power plants, you're burning coal or natural gas, but the kind of, after you do that burning of the fossil fuels, the kind of thing that comes out in the stream are, first of all, there's particulate carbon. That's certainly something we don't want to let off into the atmosphere, and so you can try and capture that. There's also small amounts of gases that lead to acid rain, and we've become reasonably good at extracting those from this flue gas. And then the new part that we'd like to add on to these power plants is some technology for grabbing the CO2 to put it underground and letting these innocuous species go off into the atmosphere, right? And so this is what we're concerned with. So here's the contents of that flue gas, and you can see most of it is nitrogen coming from the air that's being used to burn the fossil fuel. About 13% of this mixture is CO2. There's a little bit of water, oxygen, and then these minor contaminants. And so this is a low pressure gas stream. It's at about 1 atmosphere overall. And what we really want to do is get that CO2 primarily away from nitrogen, which is the bulk of this gas. And so that's not an easy separation. We need to differentiate these two molecules, CO2 and nitrogen, that are actually quite similar in their properties. They're both inert molecules for the most part, but one thing CO2 does is it reacts with amines. And so you can have this reaction with an amine to make a nitrogen-carbon bond, and that's a reaction that doesn't happen with N2. And so this is one way of just selecting the CO2 out of that gas stream. And so this is our best current technology, is using aqueous solution of molecules such as this one to grab the CO2. And the problems are manifold with this procedure. With these strong bases, corrosivity is a problem. It's a liquid. Liquids have low surface area. You're trying to interact that liquid with a gas stream that's coming out of your power plant. So surface area is an issue. There's huge needs for pure water to do this process. And then finally, there's that energy penalty of about 30%. Right? And so our goal is to try and eliminate some of these problems. And so we do have a center here at UC Berkeley and at the National Lab involving the people that you see listed. And the center is really devoted on trying to develop new materials that would be the next generation of capture materials that could lead to a smaller energy penalty for the CO2 capture. And so here you can see our two goals are really capture of CO2 from power plants, but also from natural gas deposits. And the same types of materials can probably work for both of these processes. And so we're focused on particularly compounds called metal organic frameworks and polymers. And I'll just introduce briefly these metal organic frameworks. And so these are a new class of porous solid materials that were discovered in the past 10 years. And they're composed of inorganic units connected by these organic linear bridging ligands. And so this is benzene dicarboxylate linking a little zinc-4 oxo unit. And those linkages extend in 3 dimensions and create a 3-dimensional framework which can withstand vacuum. And so when you produce this compound, it comes out of solution and it has solvent in all these little pores that you see in the structure. But like a zeolite, you can heat it up, drive out all of the guest solvent, and the structure remains intact. And so the important thing about these materials is that the result of extracting the solvent is you're left behind with a huge internal surface area for the material. And so these are surface areas higher than any other materials that are known. And so one of these compounds, if you take 1 gram of one of these compounds, this is about a gram of one of these metal organic frameworks, that gram of material can have a surface area of 5,000 or 6,000 meters squared per gram. That means 1 gram has the same surface area or even greater than a football field. Right? And so the reason that's interesting and important for these applications is that surface area is what gases will interact with, allowing you to store them more densely or capture them in a dense form. And so, for example, if you want to store methane or CO2 or acetylene in a dense form, then the best way to do it currently is to fill your pressure cylinder with one of these metal organic frameworks and then pressurize. And so here you can see some data, but the bottom line is if you fill it with this material, you can store 9 times the amount of CO2 as you would if you didn't add the material to the cylinder. All right? And so this is all coming from that surface area and the fact that the gas molecules love to stick to that surface. They love it more than they like to stick to each other. Okay, and so the question beyond storage capacity for the gases is, can we tune the surface so that it will only attract specific gas molecules in a mixture? And our mixture is going to be flue gas, and so we want to tune these surfaces to just absorb the CO2 out of the flue gas. And so one way, of course, that you could do that is to dangle amine groups off of the surface. And so we're trying to create these frameworks with dangling amines where you can have a solid adsorbent that the CO2 would stick to the surface. Another approach is actually to make frameworks where you have these exposed metal cations at the surface, right? Here is a 2+ metal cation that's accessible to the surface, and gases coming in can feel that positive charge. And the important thing here is CO2 is more polarizable than N2. It's easier to push the electrons around. And so that means CO2 will prefer to stick to the surface over N2. And you can actually adjust the energy of that interaction by changing the charge density at this metal cation site. And so we'd like to make these types of porous materials with variation of the metal cation, which is going to adjust the strength of this interaction. And the strength of that interaction is very important because it dictates the amount of energy you have to put in to get the CO2 back off and then reuse the material. Right? So regeneration, energy penalty, we're looking to lower that and yet still have a strong selectivity for CO2 bonding. And so it turns out to be very difficult to make these materials. We know these structures are possible. We can calculate that they should be stable, but the synthetic route to getting to those materials is a very labor-intensive process. We have to change many, many variables, and we can't predict the outcomes of these reactions yet very well. And it's very sensitive to things like what solvent you use or what mixtures of solvents you use. And so we now use high-throughput technology. This is a robot that's setting up reactions, and it sets up an array of about 100 reactions at a time. And so we can screen different reaction conditions and see which ones lead to our target compound. And so this is just showing you dimethylformamide with a little bit of 1-propanol gives us just the right mixture of reaction conditions to generate this framework where we've now got cobalt 2+ on the surface. Right? And all these other conditions lead to either a mixture or something else entirely. And so this speeds up the synthesis of these new materials. Then the other slow step is actually measuring the gas sorption properties. Right? And so what we'd like to do is to measure data such as this. This is just showing increasing pressure at 298 Kelvin, room temperature. And this is what we'd like to see. We want to see CO2 adsorbing while N2 has little affinity for the surface. And so we'd really like to see at this low pressure, this is the partial pressure of CO2 in the flue gas, we'd like to see as high a loading as we can get. And that loading is going to scale with the surface area of our material. But measuring this data takes a lot of time. And so one of the things that we're just starting to develop in a new project that's being funded by ARPA-E are high throughput methods for screening the products that we get from these reactions. And the first screen will involve NMR methods where the dynamics of solvent within the pores should allow us to get a profile of what the pore sizes are in these products. A lot of the outcomes of these reactions are non-porous materials, things that aren't going to be good for carbon capture. We know roughly the pore size we want. This technique should allow us to rapidly identify which of these are interesting MOFs to pursue. And then the second part that will speed things up a lot is actually measuring the gas sorption data for many compounds in parallel. And so we're building instrumentation to do that so that we can screen maybe 40 compounds at a time, and that'll speed up discovery by a factor of 40. And so with that, I'm going to hand off to Nancy Brown, and she's going to tell you about a much more difficult and less developed problem, which is trying to capture CO2 from the atmosphere, the air.
I'm going to talk to you about a very different process, and that is removal of the carbon dioxide from the air. We call this direct air capture. We use the abbreviation DAC, and I'll use that throughout the talk. And I will tell you up front that there has been very little research in this area, but it's one of great interest, and I hope I can convince you that it is important. for a number of reasons to do research in this area. I might start out by telling you that whether or not to do research in the area is quite a polarized and charged issue. There are people that believe that DAC research will lead to complacency and reduce mitigation efforts. People will think, oh, there's a solution down the way. We don't have to do anything about this. There are others that think that we need to do research to really establish the cost of DAC, and that these costs, if they're as high as people think they might be, should demolish arguments for procrastination about other mitigation efforts. I see DAC research, or we see DAC research, as a type of planet research. We think that if we're very lucky, using some of the techniques that Jeff outlined, it could lead to a significant breakthrough that might reduce the cost by a factor of 5 or 10. We also think, and I think this feeling is shared by many, that doing good research and getting good data would enable us to put a realistic ceiling on cost, and this would allow us to compare, in a relative sense, various mitigation techniques. I might say that DAC, at the cost of about $100 per ton CO2, is something that might be economically viable, especially for overshoot trajectories where the CO2 exceeds concentrations that we think are healthy for the planet. Shown before you are two schematics. The one on the right is a DAC plant that might be common to all separation technologies. Right at the middle of the diagram are two systems that are at the core of all carbon separation protocols, whether or not it concerns flue gas or natural gas or air. Each of these systems is characterized by having a CO2 absorption system, and where the CO2 is absorbed in a very sensitive and selective manner. Also is the regeneration system, where the absorbent regenerates the concentrated CO2. It passes to a compressor where it's compressed, and then it's sent to a reservoir where it's stored. Associated with all these processes are the need for energy, perhaps water, and of course emissions of CO2. And it is the energy penalties right now that are in fact the showstoppers. And on the very left of the diagram is a plant concept that has been designed by David Keith, who's one of the outstanding workers in this field. And this is the kind of plant, it would be pointing toward the atmosphere in a single direction. We've rotated one of the buildings so that you can see that it has huge fans associated with it, which take energy, to entrain the air. And this is the size of plant that you might envision to remove 1 megaton of CO2 per year. And it has a spatial need, if you will, of about 5 hectares, or 50,000 meters squared. It consists of about 10 buildings that are about 20 meters tall, that are about 250 meters long. And to calibrate what 1 megaton of CO2 a year means, a natural gas plant at about 500 megawatts generates about 1.5 megatons of CO2 a year. As large as this seems, to reduce 50 parts per million from the atmosphere over the course of 100 years, that means it's going to take us a long time to get rid of it, would require about 4,000 of these plants. And so even though this seems large, this isn't the land use problem that is associated with other mitigation techniques. So in that regard, carbon capture from air at least does not be seriously in jeopardy. There are significant challenges with removing carbon dioxide from the air. The first of these is one you might imagine. It is a huge scale problem. There are 3,000 gigatons, a gigaton is 1 billion tons, of CO2 in the air, and its concentration is about 0.04%. 1/300th of the concentration that's in a flue gas, So just think about the differences in volumes that you would have to deal with in dealing with removal from the air versus removal from flue gases. There's also a potential interferences from other gases that are in the atmosphere. In Jeff's diagram, he showed you that we could remove PM from the flue gas, we could remove NOx and SOx from the flue gas, but we can't remove these things from the air because the volumes are just too large. And when we do removal on a metal organic framework, the CO2 acts as a weak acid. Anything that's a stronger acid, like NOx and SOx and some of the acidic constituents of aerosols, are going to interfere with that removal, which compounds our problem. Another thing that is a problem is the CO2 and the concentration in the output gas, and I'll describe that in a subsequent slide. Finally, the conditions under which the removal will take place are very important and can't be controlled, so we have to be very strategic about where we locate plants. Wind velocity is important, humidity is important, the temperature of the air are all important constituents in affecting the chemistry and affecting what happens in the pores and actually affecting how we can entrain air into the capture facilities. On the slide before you, I show you the energy penalty associated with capture of CO2 on the left, on the ordinate, and it is plotted against the percent CO2 removed from the input stream. And we also see a number of curves. Each of these has a different concentration of CO2 in the input stream, and two things stand out. Number one, the larger fraction of CO2 that we remove, the larger the energy penalty. And also, the smaller the concentration of CO2 in the input stream, the larger the energy penalty. So our targets for removing CO2 from flue gas are about 90%, whereas our targets for CO2 from air are about 50%. And so that also will affect the economics. Finally, the chemistry itself has significant challenges. The good news is we learn a great deal from the work that is ongoing on removing CO2 from flue gas. And we have automated devices that are going to enable us to screen molecules for efficacy. But we have less control over conditions. Therefore, the constraints on the chemistry are much more severe. We have to synthesize new designer molecules that are effective sorbents and efficiently regenerated. The chemistry is going to be very different. They're going to be different molecules, but they're likely to reside in this class of molecules that we call metal organic frameworks. The sorbents need to be very much more selective. They need to be more sensitive and more strongly binding. Also, the regeneration is going to be more complicated because water has about on the order of 1%, air has about on the order of about 1% air in it. And the regeneration step is probably going to be more complicated as a result of this and might involve 2- or 3-step chemistry. On the slide before you, you see what I call in the center of the slide the normal evolution of a technology. You take it from basic research, it goes through R&D, through a progression of steps, and then ends up with end-of-life commissioning when you try and return the land, the water, and the air to the original conditions. In Carbon Capture 2.0, we want to change this paradigm, and we want to really facilitate the development of technologies and expedite their creation. And we're going to do that by building teams of basic researchers and people that do research in energy, environment, and economics so that they can work together to really shorten the time horizon for this development. In the horizontal part of this slide, I've indicated some of the issues that will be important for the analysis team working in concert with the basic researchers to examine in the carbon capture paradigm. They'll have to learn and continue to analyze and evaluate the energy requirements. the materials requirements as new candidate molecules become available. Does the world have enough of these chemicals to accomplish something of this large a scale? They'll have to look at the siting issues by characterizing the meteorology, making sure that, and understanding its variability, understanding atmospheric composition. NOx, for instance, in the atmosphere varies from 0.02 to about 2,000 ppb, parts per billion. Can we find areas where NOx concentrations are very low and the wind speed and wind velocity do not vary very much? Those are the kinds of questions we'll be answering. On the right-hand side of that horizontal line, we see that we have to tackle environmental issues. How much water contamination will there be? Will the other energy sources have environmental problems associated with them? How will these affect human health? How will these affect global warming potential? These questions will be answered in concert with the research and development. I'd like to focus a little bit more on the analysis by showing you the diagram in front of you. We're going to be doing a lot of modeling and building very complex modeling frameworks and systems. On the left of this diagram, you can see the various inputs for the models. We'll be looking at material stocks, water issues, energy issues. What kind of inputs do we need to drive models that will let us evaluate the energy penalties associated with DAC? What will we need to know about the contractor, the regeneration schemes? How often will we have to replenish those? How will these drive back to the materials concerns? How will we treat, we will need input composition of the atmosphere, input meteorology, and then we'll ask questions that are posed in the middle about raw material supplies, plant and manufacturing construction, operation and maintenance, and end-of-life deposition. And the output of such models will be global warming potential, human health costs. Now, how are we going to get these? I'm talking in kind of jargon. For instance, for these two, we'll probably do modeling on the continental and regional scale. It will involve solving the conservation equations of energy, mass, and momentum. We'll do this for a number of chemical species so that we can look at what the meteorology is associated with a particular site, what the gas compositions are, how they change diurnally, how they change over seasons, so that we can begin to assess how much we might be able to operate a given DAC capture plant. We will then take some of the issues associated with pollution and translate these through exposure models into human health kinds of paradigms that we can monetize. And we will do the same with global warming potential, because it will take energy to drive all these issues. I'm going to conclude with this slide and just emphasize to you that I've told you something about the difficulties in achieving direct air capture. I've also talked about its special challenges, possibilities for success, and conclude with hoping to convince you that it's important to perform research so that we can really assess its cost. Thank you.
So we're going to begin our Q&A session now, and I'm going to work this side, and my colleague Dan work this side. I have a question to start. Nancy.
Yes.
So, do you envision carbon capture units lining freeways close to a source?
Pardon me?
Carbon capture units lining freeways close to a source of carbon emissions from automobiles.
You're talking about the carbon captured trees.
I'm not gonna call it. No, you don't like that term, artificial trees. That's why I didn't use it.
I don't like it either very much. I think that we're going to have to really look for areas where the meteorology is less variable than some of the more populated areas where roads are. I also think that it might be advantageous to put carbon capture facilities very close to utility plants, so we might be able to use the waste heat from those utility plants to drive the process. So I think that those issues are going to become, trading off some of those issues back and forth are going to be important analysis concerns. It might work out well to have things near highways. You certainly have a concentrated source there, which might help. So there are going to be a lot of elements to really consider.
You also want it to be close to the place where whatever you're going to do with the CO2, right? So if you're going to put it underground, you don't want to be too far from that site. Or if you're going to make something from the CO2, you want to be near that.
This is Rich Muller. Question for Jeff. Most of the carbon in the future is going to come from power plants not yet built. And so it really makes sense to think through, as I suspect you have, separating out the nitrogen prior to it going into the plant. Could you comment on the value of that versus doing it after the burning?
Yeah, absolutely. So a lot of people think that a better way of doing this, instead of the post-combustion capture that I just showed you, is actually to do what's called oxy-fuel combustion. And that means instead of using air to burn the fossil fuel, you would use oxygen. You would extract oxygen from air, separate it from nitrogen up front, and then burn in a mixture of oxygen and CO2. And then all of the flue gas, all of the emissions, you would then store underground. And so the reason that might make more sense is that we can possibly retrofit existing power plants that with this technology, in addition to building new ones using it. But the reason it makes some sense is that the concentration of CO2 post-combustion is about 15%, 10 to 15%. And part of the difficulties and the reason there's this big energy penalty is that it's this low concentration. A low partial pressure means you need a very steep absorption isotherm, and that means you're going to have to pay the price to get the CO2 back off. But oxygen is at a higher concentration in air. It's about 20% of air is oxygen. And so that's actually an easier separation for that reason. And it's also chemically a different problem. We can, in fact, use charge transfer chemistry and electron transfer from metal sites on a surface to selectively bind O2 over N2. Right? And so it's a different chemical problem, but because of the higher concentration of oxygen in air, and also, I should say, because we don't have to get all the oxygen out of air, it makes sense. Right? For CO2 from post-combustion flue gas, you really want to try and get almost all of the CO2 out of that stream. If you're just taking oxygen out of air to feed it into a power plant, it's okay if you just grab 50% or 70% of the oxygen from the air. As long as it's pure oxygen, that's okay. You can feed in more air. Does that make sense?
Do you have a question?
Yeah.
Have you considered combining wind power generation with the carbon capture from air?
There are studies about the energy penalties and the additional energy that needs to be supplied. And one thought is that renewables would be very, very attractive. In fact, if you use fossil fuels and it's real expensive with respect to energy penalties, you reach a point of diminishing returns very, very quickly where you almost have negative forcing ability. I mean, it's...
I'm thinking beyond that, actually, you need forced air pushing something, so a place where you put a wind turbine.
Yes.
It's a good place also, presumably, for capturing carbon from air.
Yes.
So as opposed to having two things, one supplying the other one, having the same thing.
Yes.
Doing the same thing.
And people talk about that, and you remember the diagram I showed you by Keith that showed those large fans. If you could use the wind judiciously, you would not need those fans.
I was wondering if you could do a quick comparison of carbon capture from the atmosphere in the buildings that you've proposed versus the sort of natural carbon capture that occurs in quick-growing plants and that sort of type of carbon capture.
Your question is an excellent one because that's what needs to be done. However, the price of carbon capture from the air is all over the place. It goes from $300 a ton of CO2 to $1,000 per ton of CO2. The problem is what everyone means by a ton of CO2 is somewhat different. Many people use the term avoided CO2. That's very nice, but then avoided CO2, they take a certain amount out of the atmosphere, and then they generate energy to drive the process. And those people don't really recognize what percent of that CO2 ends up in the atmosphere. Do you understand? And so the numbers aren't very meaningful. And so I think to do the comparison that you're speaking about, which needs to be done, you need to get these numbers cleaned up a great deal first.
So a possible area of research.
Yes, it is, and an important one.
Question for Jeff. I'm over here.
Where's over here?
Over here. I understand that you identified a material that has a high surface area and is good for doing what you wanted to do. But then you subsequently showed that same material filling a fairly traditional looking pressure vessel. So can this material work at atmospheric pressure in capturing carbon dioxide, or do you have to have it in a tank under pressure?
Right. That's a good question. And actually, you don't want to have to pressurize the flue gas. This is a huge volume of flue gas, and most of it's nitrogen. We don't want to have to compress that to do our separation. And the gas absorption isotherms that I showed you were below 1 atmosphere. And so it does work to grab CO2 at these very low partial pressures, 15% of 1 atmosphere being CO2. So it's critical that we can do it at these low pressures. So those were 2 separate applications. Storage, we can do at high pressure and get a very high energy, a very high density. The separation is a separate application. We want to do that at low pressure.
Another question for Jeff. Even though, over here, although the project is still in its initial stages, have any industries at all shown any interest in the project, or?
There's actually a lot of researchers around the world working on these types of no-organic frameworks for gas separations, and many people are working on CO2. And yes, companies do show interest, and people from venture capital at least stop by very regularly. I talked to somebody this morning asking, all right, how long before we can sell this technology? I'm actually the worst person to ask that question, because I just know about discovering new compounds in the lab and characterizing them. And people at Berkeley Lab are much more qualified, such as Nancy, to actually do the economic analysis of, does this make sense to start putting into a really wide-scale application. So I don't know if you want to comment on it.
No, I think that's the answer, yeah.
Hi.
The light is so bright.
I asked my 7th graders with a very broad thing, how would you handle CO2? What would you do? And one really bright student said, why don't we just unplug the power plants, fossil fuel power plants, and just unplug them and turn it on? How simple is that? There is no cost involved, except someone isn't making any money. Why haven't those avenues of the brilliance of my 7th grader been even looked at? Just unplug it.
Well, you wouldn't be in this room watching this presentation. But actually that's a great solution if everybody on the planet's willing to going back to really doing without electricity and heat. So there are real costs to shutting off all these power plants, because we don't have the energy sources in place to live the way we do right now. And you have to convince not just the U.S. to do that, but it's not, you got to convince China and India and people around the world to do that. Ultimately, we do need to do that.
I have another question for Jeff. I think you mentioned as a final, where you're going to place a CO2, you would inject it underground. Is that correct? Is that what you said? So my question is, what would you do to prevent, say, you know, if there were an earthquake or some shift in the ground that could actually re-release the gas into the atmosphere?
That's a great question, and in fact, there is a center here at LBL led by Don Paula, who's up here, which is devoted to trying to understand all the issues associated with carbon storage underground, and it means you have to have expert geologists and geophysicists who can really identify the best sites for where to put the CO2 to make sure there's not going to be some catastrophic event, earthquake maybe, but also to make sure it doesn't come back up, right? You know, if we put it underground, we want to make sure it's not coming back up. And we have to have ways of monitoring it. But this is an important area of research, and a lot of the best research is going on here at LBL.
Hi, I was wondering, maybe I misread, but it seemed like there was a discrepancy between the 30% energy overhead that was presented earlier, and then later the percentages were 3-4%. Were those measuring different things, or what's the difference between those two?
Yeah. First of all, the plot I showed you, even though I was talking about direct air capture, was for capture from flue gas. But the gist of the story is the same. But the concentrations that you were seeing on that plot were relevant for flue gas. But the conclusions derived from the plot are the same, independent of where you're doing the separation. Does that answer? Let me tell you that those penalties, those thermodynamic limits, industry typically operates about at a factor of 3 to 5 times greater than those penalties. And so what we would like to do is get capture from flue gas to be about, DOE's target's about $25 per ton, and the target for DAC is about $100 per ton. And that's still real expensive for direct air capture.
I think maybe the question maybe pertains to those curves were thermodynamic. That's the best you can do. That's not what we actually do with the current materials. And so those were the limits. We hope we can get down to those low percentages, but that's not what we can do currently.
Any other questions? Howard, wait.
Yes.
Mike's coming.
Do you want to pass this back and forth?
Yeah, thanks.
I was wondering what the potential is for using artificial photosynthesis as a DAC method, or is that even under consideration?
Well, it certainly is a way to remove CO2 from the air. There are other mitigation techniques as well, like forestation, afforestation, where we grow trees for a while, chop them up and put them back in the soil. There are many of these things, and as an earlier question was posed, what are the relative cost of that? And I argue that those do need to be compared, but it's not possible to do so right now.
Okay, any other questions? 3 up, here we go. Okay. Get to count down to number 2.
This one is for Jeff. You were talking about putting the CO2 underground, but doesn't that have like a long-term effect on the earth? Because if you're putting it on the earth, you're just gonna keep putting them bottling down there, but at a point it has to come out because there's not a lot of earth to keep on bottling it down there. Doesn't it have an effect on the earth itself?
Yeah, it can. And so understanding the chemistry involved with CO2 when you put it underground is also important research. I guess the idea is that, you know, things like oil and water there are large formations underground under, you know, certain types of rock, and it stays there for hundreds and thousands of years. And the idea is that we want to put CO2 into those formations where it really will just be protected under this geologic formation and not be able to percolate back up. And so there are formations that should be able to do that. And so things like You know, in oil recovery, currently, you can replace the oil with CO2. But also you can do this with, say, saltwater aquifers and maybe replace water with CO2.
Okay, any other questions? 3, 2, oh, there's one right here.
Hi, sorry for the accent. I would like to know, I heard about that there is a process with microalgae which can absorb CO2, from the power plant, and after we can use those microalgae to create like oil or stuff. Why, instead of filter the CO2 and try to store it, why don't use those microalgae just to absorb the CO2 and avoid all the process of compress the CO2 and store the CO2 into the ground?
Let me see if I understand. Why not use microalgae?
Yes.
You know, I don't know enough about the specifics of microalgae to really give you a good answer. I think, but only to say that there are a lot of potential mitigation approaches that are on the table, but I do not know the specifics of that one. Maybe Jeff, do you?
Yeah, I'm not an expert on that either. There are people studying possible, you know, using biology and growing plants to mitigate CO2, and you have to take into account the water needs and the nutrients and, you know, how long it actually is going to be tied up in the plants. You know, some things don't. You know, after it dies, it decomposes and the CO2 goes back into the atmosphere often. So they're all complicated possible solutions, but people are studying those things.
So there's another question up here.
I have a question for Nancy. My research focuses on carbon capture. I want to know when you capture CO2 from air, because CO2 concentration is very low. As we know, when we capture CO2 from flue gas, CO2 concentration is about 15%. Among all of the kind of solvent, ME should be a better one. But if you capture CO2 from air, because the concentration is very low, do you have some good idea about that? If not, maybe you need a lot of space to deal with CO2.
I think the question was essentially how could we, what kind of materials could we use to capture CO2 from air? Is that right? I mean, so the idea is that when you have this very low concentration of the CO2 in air, it means that if you look at that gas sorption profile of pressure increasing and the uptake, you need at this incredibly low pressure to have some capacity for the material absorbing CO2. And so that means a very strong interaction, and that means a very strong base. And so the thing about amine molecules is that we can actually tune the basicity, we can change the organic groups on the nitrogen and adjust the energy of the interaction between CO2 and nitrogen. But if you have a very strong base, then you can get materials that will absorb CO2 from the atmosphere.
Okay, now any other questions? 3, 2, 1. Okay, I guess not. Jeff and Nancy, thank you very much. This is a difficult topic.